Okay, great. I'm at Berkeley time, so I can start. Okay. So today we're going to talk more about duality and continue to talk about kind of different perspectives on duality. And hopefully by doing more and more examples and hearing about the same thing in different ways, all of this will kind of crystallize and become clearer for all of you. Okay? So the last time we talked about the following, right? We have P star, which is the min f naught of x, such that fi of x that's equal to 0, hi of x is equal to 0. And now we also showed something else, right? We talked about what this is in terms of the Lagrangian, right? First we had just introduced the Lagrangian as, oh, here's something you do to modify your primal. But we actually showed that we can write this as min over x max over lambda and nu of L of x lambda and nu, right? And then when I had my dual, this was my max. Right? This was the kind of thing that we showed last time. And we talked about the min-max inequality, right? That showed that basically the primal is always lower bounded by the dual. Everyone remember this? P star is always greater than or equal to D star. We saw this through the min-max inequality last lecture. The lecture before that, we proved this through a completely different route, right? Where we showed that this function g must always be a concave function, therefore the dual is always a convex function. And we showed that g is going to always be, all of the g's are always going to be lower bounds for P star, and therefore the best lower bound is also a lower bound, right? Everyone remember this kind of picture? Right? And then last time we showed that, oh, we can write this as, oh, sorry, I should have a max min right here. Oops. Last time we showed that this min-max and max-min are two other ways in which we can write the primal and the dual. Kind of coming back to everyone? Okay. So now what I want to introduce is the concept of strong duality. And strong duality is the special case where P star is exactly equal to D star. And we saw this in the case of the min norm problem, for example, that we did on the first day. We saw that P star was equal to D star in that case. And then last time we did this example of the partitioning problem. And there we did not necessarily have strong duality holding, right? So you've seen these two different examples. In general, strong duality holding is a wonderful, wonderful thing, right? Because that means that you can get the optimal value by solving the primal or by solving the dual. It's not that the dual just gives you a lower bound. It actually gives you the exact same thing that you want, okay? So wouldn't it be really nice if we knew when strong duality held before solving the entire problem, right? If we had to compute P star and we had to compute d star to check if strong duality holds, well, that's kind of a lot of work, right? But if we could just compute d star and then say because strong duality holds, it must be equal to p star, that's really convenient, right? So for this, I'm going to introduce to you conditions for strong duality. Okay? And the most important one, I can't spell, not Salter, Slater. S-L-A-T-E-R. So there are different conditions for strong duality. In this class, and most people use this one condition, which is called Slater's condition. So Slater's condition holds for a certain set of problems. First, you have to have a convex problem. That means that your objective function must be convex and your domain must be convex. Your constraints must be convex, right? So if I have a convex problem, so for example, let's say p star is equal to min f naught of x, fi of x less than or equal to 0. Okay? And there exists some point x naught in the domain and x naught belongs to the relative interior of the domain, and it's called strict feasibility. Then strong duality holds. Okay, so let me walk you through what this means. So I have a convex problem, right? First thing you got to check, is your problem convex? Otherwise, Slater's condition is not going to hold. Next thing you have to check, okay? You have to find some point x naught such that this belongs to not just the domain, but the relative interior of the domain, okay? So what does the relative interior of the domain mean? Let's think about this picture here. This is a circle, okay? This is a circle in R2, right? It's in the 2D plane. What's the interior of the circle? Is this point in the interior of the circle? Yeah. Is this point in the interior of the circle? No, right? This is on the boundary. Okay, is this point in the interior of the circle? Definitely not, right? So anything that is strictly inside is called the interior, okay? This is something that you all understand, you've all seen before, you understand. What we're talking about here is the relative interior, okay? So now, instead of thinking of this circle in two-dimensional space, let's think of this circle as embedded in three-dimensional space. Okay? So now in R3, what does it mean for something to have an interior? If I gave you a sphere, right? Or let's say I have my coffee cup here. In R3, what's the interior of this coffee cup? Well, it's inside the cup, right? It's not on the boundary, it's not outside, it's inside where the coffee is, right? But now, if I consider, so it's a three-dimensional volume, right? That the interior is a three-dimensional volume. When I embed this circle into a three-dimensional space, does it have an interior?
No.
Is there any three-dimensional volume contained inside of it? It's all boundary, right? The circle is all boundary. Everything is a surface.
Because it's still 2D, right?
It's still, the circle is still 2D, right? I can have a 2D object in 3D space, like, that's obviously true, right? You can have a piece of paper that exists in our three-dimensional world. So now, this concept of interior is doesn't quite make sense, right? When you think about interior, what you want is to happen, you want to say like, no, even if the circle is in 3D space, obviously the interior of the circle, I mean, is what's inside the circle, right? Even if it's, whether I consider it in 2D space or 3D space, that interior notion should be the same. So the relative interior is basically the interior with respect to the affine subspace that your object can be embedded in. So the easiest way to understand this is to think about, when you think about the circle embedded in 3D space, you still want to think about the natural interior as the interior. That's the relative interior. It's the interior relative to the kind of inherent dimensionality of the thing itself, right? So basically, don't discount its interior just because it's a 2D thing embedded in a 3D space. Does that make sense? Like, this is something that I don't want to go into too much of the formal definition of what a relative interior is, because that requires us to go into too much kind of analysis and geometry. But this is the key concept and idea, okay? Does that make sense to everyone? What we're trying to get at? So, we're not going to try and trip you up by tricking you between the relative interior and the interior. That's like not the kind of question that we're going to try to give you in this class. But at the same time, it's really important for you to understand the difference between these things, okay? So most of the times when you're dealing with any kind of optimization problem, the interior and the relative interior are going to be the same, okay? But there will be cases when it's not. Everyone good with relative interior? Okay, good. So now we have this relative interior. And now I want to say that I want to find a point that is not on the boundary, but is strictly feasible. So what that means is I want to have all of these inequalities satisfied strictly. Not just, not with equality, right? So I need to find something in the interior that basically is fully satisfying my constraints, okay? And in particular, the inequality constraints. The equality constraints I'm not caring about, okay? In particular, because when I've constrained this to be a convex problem, these are all going to be affine, okay? So if I have a strictly feasible point in the interior, in the relative interior, then I can say Slater's condition holds, which means that strong duality holds, okay? So this is something that you can check without ever having to solve the problem, right? This is something that is just about what is the domain, what are the points in the domain, okay? What is an affine subspace? So an affine subspace is basically a translation of a hyperplane. So a hyperplane must always pass through the origin, but an affine subspace is not a vector space because it doesn't pass through the origin, but it still has that nature. It's like a translation. So it's the domain of the problem. So implicitly, remember when we talked about convexity and we talked about these problems, we said that implicitly the domain of Fi and the domain of Hi give a domain for the particular problem, right? So that's what the domain means. Of the domain, yes. Domain D. Yes. Doesn't the x also have to be, or this should be x naught? The question is, does this also have to satisfy this constraint? So because we want this to be a feasible point, it will, by being in the domain, it's going to satisfy that. but it's the inequality that must be satisfied strictly. Saying that it's in the domain is, if it's a feasible point, that implies that it's in the domain, yes. No, it has to be a feasible point. This is like, how should I say? Maybe I should make it clear. Some feasible point. What is the difference between x naught belongs to relative interior and? So I can perfectly be in the domain and be a feasible point by being less than or equal to 0. There's a strict inequality there. There's not a strict inequality here. So these are different things. It's not in the bound, but there might be a different, like you might have a boundary that is coming from a different constraint. Does x in the relative interior means x is feasible? X has to be, for x to be in the, no, these are two different things. For feasible, you have to have both of these conditions satisfied, or all of these conditions satisfied. You might have a point in your domain that is not feasible. Right? Your domain is something that could be different. Okay, so there will be lots of examples on this, but I just want to give you this introduction. That's first condition. The second condition that I want to introduce is what is called refined Slater's condition. Okay? And now I have everything as before, so I have a convex problem. Except now I also have F1, F2, Fm are all affine. Okay? So here I could have anything, right? This could be nonlinear, they could be whatever. And as long as I find a point in the relative interior that is strictly feasible, I'm good. Now, what we need to do is we need to make sure that strict feasibility holds for just one point, so for one inequality. So now, strong duality holds if there exists x naught such that okay? So strong duality holds if I can find an x naught such that it's strictly feasible for at least one of the inequalities. You don't have to have it true for every single one. And here I'm saying that, okay, like let's say the first k ones are satisfied with the less than or equal to, and then the remaining ones are strictly feasible, right? But there's no condition on this k. So as long as you have one, you're good. Does that make sense to everyone? This is what is called the refined Slater's condition. Here you don't have to worry about relative interior or nothing. Basically, you just need to find a strictly feasible point that is strictly feasible by one of the inequalities. Is this a harder condition to do it? Actually, it's easier, right? I mean, it depends on how you see it. It's like you might not have affine conditions, right? So it's just for a different case. Okay, good. So there will be a lot of examples on this. But now I want to find the dual of a particular example in a case where strong duality actually holds. Something that will be helpful on your homework, actually. Okay? So now if I have a linear program, right? What is a linear program? A linear program is an optimization problem where both the objective and all of the constraints are linear. So let's consider, for example, minimize C transpose X subject to AX less than or equal to B. Right? And so I'm saying, I'm using this, anyway. So here, now look at all of my constraints. Right? My constraints are linear. My objective is linear. This is a linear program, right? Everyone with me? Okay, good. So now let's go about finding the dual of this. So now you've done this a couple of times. I'm going to give you a minute and let you compute the dual. Okay, that was a 1 minute and 30-second timer. So how many people have the Lagrangian written down? Okay, so what do you observe about the Lagrangian? There's no equality constraints. Okay, good. There's just an inequality constraint. What are different values that the Lagrangian can take? Actually, before we get into that, let's just look at this problem for a minute, okay? So implicitly now, I haven't written out a domain explicitly here, right? But what is the domain for x in this problem? If there's no constraints given. It's Rn, right? So now, what is the interior of Rn? Just any point, right? As long as you're not infinity, you're in the interior of Rn, right? So finding the interior, relative interior, all things are easy in this case. Here, would you want to apply refined Slater's condition or Slater's condition? What is the nature of your FIs? They're affine, right? So now I just need to say that somewhere here, one of these AX, so this is basically this thing, is the same as AI transpose X less than or equal to BI, right? If A, these are the rows of AI, of A. Okay, this is just, these are all of my, the number of rows is the number of my constraints. So I just need to find one of these that is strictly feasible, right? Do you think that's possible? So if I can find a feasible point, I can also find a point that is strictly feasible, right? Because I can always perturb x by just a little bit and make that point into a strictly feasible one, because there's no constraints on my domain, right? Because x is anything in Rn. And so this, I can say, refined Slater will always hold for this. Does that make sense to everyone? Because I just need to find something. So for example, what if BI was like, let's say B1 was 1, right? And this is now something times x is less than or equal to 1. I can always find some x. For example, I can find, if this was positive, I can always put x equal to 0, right? And find something like that. Do you see what, does that make sense to everyone? So in this case, I can say that strong duality is going to hold. And in general, for linear programs, as long as your linear program is feasible, basically as long as your domain is not empty, strong duality will always hold for linear programs. Okay? So we expect in this case to have P star and D star be equal. As long as your AX is less than or equal to B is not some kind of pathological thing where it's not possible for it to hold, where the domain itself is empty. Make sense? Yes, question?
Could you repeat how we got this strict inequality from this?
So for example, I'm just giving you an example. If BI was 1, B1 was 1, right? I could choose x equal to 0. This is a feasible point, and I'm good. let's say B1 was -1, okay? Well, I can check and see that I can look at, for example, whatever this is, and I know I can, for example, x is again anything. I could choose x to be exactly I could choose x to be exactly in the direction of AI, right? Times some negative constant, and then I could get this to be any quantity I wanted, right? So I can always generate a strictly feasible point for this. Does everyone see that? Right? Do it out for some examples, which will help. Okay? So refined Slater will hold, which means that strong duality will hold. And by extension, basically, strong duality will always hold for any LP, which is, again, as I said, has a non-empty domain. So if there's something pathological about this that doesn't allow the inequality to hold, for example, if there's some inconsistency in the rows of A that makes it so that this is completely impossible, like if you're asking for, A transpose X to be greater than 0 and A transpose X to be less than 0, which you could come up with pathological constraints of that form, and then you would have an empty domain, then strong duality might not hold, right? But in all other cases, for a linear program, strong duality will hold. Okay? Good. So now, what did you have as the Lagrangian for this? As you pointed out, there's no equality constraints. So what do I do here? Now, I'm not going to write anything unless someone shouts it out, because now I'm expecting that we've done duals for a little bit. I want to make sure that everyone's with me. What's the first term? Very good, right? So now I want to, what's the next step I want to do? I want to be minimizing this over x. So how is it going to be useful for me to reorganize this expression? Bring all the x's together, right? So how do I do that? So I have a minus B transpose lambda, plus I have an A lambda transpose plus C transpose times x, right?
Wasn't it lambda transpose A?
Yeah, sorry. Lambda transpose A, thank you. That's my bad. Okay, good. So now, when I'm looking at this,
Shouldn't it also be lambda transpose B?
it's a dot product, doesn't matter.
Oh, okay.
So now, when I'm going to do a minimization, I'm going to write g of lambda is equal to min over x of L of this Lagrangian. Okay? So now I'm looking at this thing. And this is now a function that is affine in x, right? There's a constant. And then there's some scaling factor. There's some slope, and then there's x. So how small can I make this? Arbitrarily small, right? What's the smallest thing I can drive this to be? Negative infinity. So what is this going to be equal to? Negative infinity. Is there any case in which I won't be able to take it to negative infinity?
That one is 0.
What thing is 0? If this is 0, can I take this to negative infinity? No, right? So I have two cases now. So I have lambda transpose A plus C transpose not equal to 0. Or if this is exactly equal to 0, then what is the value of this? What is the min? Is there any x here? So what is this? right? So these are my two cases now. Now, you've seen this kind of thing happen before, right? So now what am I going to do for my dual? I'm going to try to maximize my g of lambda.
With respect to lambda.
Do I ever want to have my maximum be negative infinity?
No.
Am I ever going to choose a lambda that, like, which of these two values? If I wanted to choose the largest one, which one do I prefer?
Second.
Clearly this, right? It's always better than negative infinity. So I'm always going to choose a lambda that satisfies this constraint. Right? So my dual, one second. Let me just do this. Maybe I'll just fit it here. So, okay. So my dual now is the max over lambda greater than or equal to 0 of negative B transpose lambda subject to the constraint lambda transpose A plus C transpose is equal to 0. More commonly, people often like to kind of transpose this and write this as A transpose lambda plus C equal to 0. Just take the whole transpose of this whole thing. You can see that this is completely equivalent. But somehow this is the more common way of writing this constraint. It doesn't matter which way you write it. You're calculating the gradient of this with respect to x and or you're saying that another way to find the minimum of this is to observe that, okay, well, this is a convex function of x. You can compute the gradient of this and set it equal to 0.
Yeah.
And then the minimum will be attained when the gradient of this is equal to 0. Yes, but that will always take you to negative infinity, though.
Yeah.
Right? Because here you're like this maximization aspect is getting a little lost there. Because there your gradient will either be 0 if this is 0. And so again, actually, you'll get the same cases. Yeah, it'll be equivalent if you break it down carefully. It'll be exactly the same way. Okay, good. So now we have this dual. The homework is the dual of the dual. So what you have to do is find the dual of now this problem, right? And you'll see some interesting results on the homework. I'm not going to spoil it for you. You should do it on your own. Okay, good. So with this now, I want to introduce you to another perspective on duality. So if you recall the very first lecture I gave in this class, I said that the foundations of optimization were built not to optimize large language models, right? The foundation of optimization came far earlier than this, and a lot of it came from resource allocations and operations research types of problems. So basically, you're running some kind of business, and you want to make money, right? It's like the basic thing. And you have constraints. You have a profit, or you have, and you want to maximize that profit subject to the constraints that you have, okay? And so what we're going to talk about now is this economic interpretation of duality, which is something that is extremely powerful and valuable and used quite regularly, okay? So for this, let's consider an example. And let's consider the hypothetical scenario that we all decide that, okay, we're going to quit this engineering business, not worth it, and go into making real money. And what we're going to do is we're going to make wine. You'll quickly see from this example why I'm an academic and not in the money-making business. But hang with me for the rest of this example, okay? So let's say you've decided to go into winemaking, and you've acquired grapes, okay? I know that you need grapes to make wine. So let's say you have 200 kilos of Merlot grapes, and and you want to decide what kinds of wine to make. And then someone tells you, oh, there's some really nice blends you can make. You can make Merlot Shiraz blends that do really well in the market. Okay? So you have blend 1. And this requires 4 kilos of Merlot to 1 kilo of Shiraz. And this sells for $1.20 a bottle. Okay? Or I could have 2 kilos of Merlot plus 3 kilos of Shiraz. And this sells for $15 a bottle. Okay? Let's say this is our setup. Now the question is, what are the quantities you should make of each kind of wine, right? Let's say we can name these blends, blend 1, blend 2. What is blend 1? Anyone have any names for any wine connoisseurs in the room? What? Champagne? Okay, we can call this red champagne. You're all showing that you also should be engineers and not winemakers. What's the second one? Napa Valley, okay. Good. Okay. So why don't you write this now as an optimization problem? What is the optimization problem you're going to try to solve? So what's the optimization problem? Let's say I want to make Q1 bottles of blend 1 of red champagne and Q2 bottles of Napa Valley, right? So how much money, what do I want to do? Do I want to maximize or minimize? I want to maximize my money. Maximize over Q1, Q2. And I want to say, well, I get 20 times Q1 plus 15 times Q2, right, for every bottle I make. And can I make as many bottles as I want of this? No. What is my constraint? I have, how many grapes do I use per bottle of red champagne? Well, I have 4 times Q1 plus, so I guess I have a constraint for the total amount of Merlot I have and a constraint for the total amount of Shiraz I have, right? So if I make Q1, I use up 4 Q1 of Merlot, and then if I make Q2 of Napa Valley, then I use up 2 Q2 of Merlot, right? So this better be less than or equal to 200. This is my constraint on Merlot. And I have 300 kilos of Shiraz, so my total Shiraz had better be less than 300. I use up Q1 per blend of red champagne, and I use up 3 Q2 per Napa Valley. So this is my Shiraz constraint. Right? This is the optimization problem I'm going to try to solve. What kind of problem is this? This is an LP, right? It's a linear program. Very similar to this. I have linear objective function, linear constraints. Except I've written it as a maximization, right? Not as a minimization. Do we also need Q1 and Q2 to be non-negative? Great question. We could enforce a constraint on Q1 and Q2 being non-negative as well. Because, well, why would you make negative quantities of bottles, right? Given that we're writing this as a maximization, we're naturally incentivized to do that anyway. Because, you know, you would never, if I made negative bottles, I'm just going to lose money. So, but then you had to account for the fact that, so the question is, couldn't making negative bottles give you resources that could then be used in some other way? So basically you're saying buy bottles of wine and do something with the grapes, right? So hold that thought. We're going to come to that. It's a very valid way to think, and we're going to come to that. So just keep that in mind, but we're not going to think about it exactly that way. So of course, if you notice that there's a simplification that we're doing here, right? We're treating our bottles of wine and our grapes as somewhat interchangeable. Like, of course, there's processing costs. We're not taking into account, like, the fact that there's cost to make this wine, there's cost to transport this wine, there's cost to store this wine. You have to have someone in the store, and you have to pay the person to be able to sell the wine. Like, there's so much more that goes into a business, right? This is obviously a toy problem constructed for us to be able to explore this. So we're assuming in some sense that all these other costs are vanished away. Just so that we can compare, I want to write this as a minimization problem. And so if I wanted to maximize, right, if I'm trying to find the argmax of some f naught of x, right? Let's say the f naught of x has some shape, whatever it is, okay? I could alternatively consider negative f naught of x, right? Just reflect it. And I could look at the argmin of that, right? So these are effectively the same problem, right? So I could instead equivalently consider minimize minus 20 Q1 minus 15 Q2, subject to the same constraints. And the answers that I'd get out for Q1 and Q2 would be the same thing, right? The minimum and the maximum would have the opposite sign, but the Q1, Q2 I'm going to get out is going to be exactly the same. Does everyone see that? So just so that we can compare with this later on, I'm going to consider this minimization problem, because you're saying that I want to, like, minimize the negative of my profit instead of maximizing my profit. Makes no difference, okay? You could do the exact same thing with a maximization problem, but just because I find it easier to, students tend to get confused if I keep switching from maximization and minimization, so I'm not going to do that. So now, let's build on the question that was asked at the back, okay? And the question was, well, look, clearly you are no good at business. You didn't say that, but, you know, I'll announce it. Probably I'm not good at business. Why don't you just try to sell off these grapes instead, right? Instead of bothering with making these bottles of wine, just sell the stuff, take your money and run, right? Why bother? And so that's one option. Another option is, like, maybe, despite all odds, I'm brilliant at this, and it's totally worth my time to actually buy more grapes, right? Get more grapes and make even more and more and more bottles of wine, right? What if I kind of incorporate the price of these grapes into what I'm trying to do, okay? So let's say I could, I have a price lambda 1 for and I have a price lambda 2 okay. So now maybe what I want to do is I can say that, hey, I can make some bottles of wine. Maybe I want to make some bottles of wine. Maybe I want to make some wine and sell some of the grapes. Maybe I want to buy more grapes and make even more bottles of wine. Can I write an optimization problem that kind of brings all of this together, right? So what I'm going to do is I'm going to say, well, I have my old optimization problem. I have min over Q1 and Q2 minus 20 Q1 minus 15 Q2, okay? And now I'm going to say at price lambda 1, I'm going to look at, well, 4Q1 minus or plus 2Q2 okay. So what is this quantity here? 4Q1 plus 2Q2 minus 200. So 200 is the total kilos of Merlot grapes that I have, right? 4Q1 plus 2Q2 is what I use. Okay? So if I use, let's say I use more than 200, right? Then I'm going to have to buy those extra grapes at price lambda 1. Right? And so that's going to be a cost additional that I have to consider. Instead, alternatively, what if I could sell off some of those grapes, right? Then I could get lambda 1 for each of these, and this would then be a negative quantity, right? Okay? Plus, similarly, price lambda 2 for Q1 plus 3Q2 minus 300, right? So basically, I'm saying, hey, I can buy more grapes and maybe make more bottles, right? And that will maybe get me better, get me in a better place. Does everyone see that? Right? And I can just rewrite this. Minimization over Q1, Q2. And just pulling all the Q1, Q2 terms together, I get minus 20 plus 4 lambda 1 plus lambda 2 times Q1 plus, what do I get? Minus 15 minus 2 lambda 2 plus minus 2 lambda 1. Am I doing this right? Minus 15, I have plus 2 lambda 2 plus 3 plus 3 lambda 2 times Q2 minus 200 lambda 1 minus 300 lambda 2. Okay? So I just did some rearrangement of the algebra here, nothing particularly fancy. Okay? But what is this starting to look like to you? what is that expression up there looking like to you? It's looking like the Lagrangian, right? So what the Lagrangian is trying to say is it's saying, hey, maybe you're so good at this business, you're so good at this optimization. If you could violate your constraint by a little bit, right? Even if you could pay the price lambda 1 for every unit, like lambda 1 per unit of violation of constraint, maybe that's something worth considering, right? This is the price that you're willing to pay to violate the constraint, is kind of what this is trying to tell you. Okay? And this is the optimization problem that you get. So let's just pause for a minute. Does everyone see that this, what we've gotten up here is the Lagrangian? Even though we started out not trying to write a Lagrangian, we started out saying, hey, maybe we can buy more grapes and do better, right? Okay, so now further, can we think about what if, in fact, I should not be getting into this business at all? What is my indifference point? What is the point at which I don't care if I just sell all the grapes that I have, or I try to make those grapes into bottles of wine? Okay? How would I make that decision based on what I have here? What is the point which I don't care at all? Under what condition, when I look at this, does it not matter what the value of Q1 and Q2 are? So if I look at this thing, I've written it out in terms of Q1 and Q2. If both of those things, if both of the coefficients of Q1 and Q2 are 0, what is my profit going to be under this model, right? It has no dependence on Q1 and Q2, right? That's kind of my indifference point. Like, I don't care if I make wine, nor do I care if I make, if I just sell off my grapes, right? Just like the exchange point for where my raw materials are exactly interchangeable into the bottles of wine. Okay? So if both of those were 0, how much money would I make? I would make minus 200 lambda 1 minus 300 lambda 2, right? Okay. So what is the best case scenario that I would get here? If I wanted to maximize this, I could write this as a max subject to and minus 15 this is basically the best I could do at my indifference point, right? So I'm saying constrained on being indifferent to either making wine or selling off all of my grapes. This is the best money I can make, right? This is the maximum of that bound. But what is this exactly equal to? This is exactly this dual formulation that I have for the LP. Right? What's up there is exactly minus B transpose lambda. Right, what was your B over there? 200, 300. Exactly negative B transpose lambda. What you have here is exactly the same constraint. Right? So the dual, in a sense, is looking at what is that indifference point for you. Okay? So this interpretation and this perspective on the Lagrange multipliers or the dual is what is called the shadow price interpretation. It's basically saying that the Lagrange multipliers, lambdas, are saying how much are you willing to pay to be able to violate a constraint? Okay? Like, is it worth it to you to cross this constraint just by a little bit? And so by looking, in some sense, at the magnitude of the Lagrange multipliers, it can tell you the importance of the constraint. Okay? So something that has a Lagrange multiplier that's very close to 0, and we'll see exactly what happens when the Lagrange multiplier is 0 very shortly, is a constraint that is not particularly important. But something that has a lambda that's larger than 0 is going to have a constraint that's very important. Okay? So this is the economic shadow price interpretation. So remember what we did was we had this maximization, but we said instead of considering this maximization, I rewrote this as this minimization. And we're considering the dual of this now, so that basically it's easy to compare with the dual that we got here. But all of this would still hold if you went through this with the maximization as well. There's no difference. But we're thinking now of this as this minimization. So this is basically, it's not anything different from what we've seen before. It's the same kind of thing, but we're trying to show it to you in different perspectives. Okay? Okay, I'm going to introduce you to one more thing that basically connects to this very, very closely. And this is called okay? So let's consider a problem, optimization problem, where strong duality holds. Okay? And I want to try and understand what happens at the optimum points. So I want to consider my optimum x star, my optimum lambda star, and my optimum nu star. Okay? So my optimum primal variables as well as my optimum dual variables. Okay? So I know that P star is equal to F naught of x star, right? X star by definition is going to be a feasible point, so x star obviously satisfies all of my constraints. I'm not going to rewrite all of those. D star is equal to my G of lambda star and nu star. Okay, so this is my primal optimal point. This is my dual optimal point. If I have strong duality holding, this implies that F naught of x star equal to G of lambda star and nu star, right? Just by the fact that P star equal to D star. Nothing fancy going on there. Okay? What is G equal to? Well, G is our minimum of the Lagrangian, right? So it's the min over x of the function L of x comma lambda star comma nu star, right? Instead of writing it out, can I just write out here F naught of x plus, let's say, sigma this is just equal, right, by definition. This is by the definition of G. Okay? let's look at this quantity. I want to relate it back to x star. I'm looking at this min over x of this function. Okay? So the minimum of this function is going to always be smaller than that function evaluated at any particular point, right? Okay? So this is always going to be less than or equal to. So min of a function less than or equal to evaluation at a point. So I can rewrite this as f naught at, let's say, what is the point of interest? Where do I want to evaluate this? X star, right? I'm just going to pick some point. So just by the fact that this is the case, I can write this is less than or equal to this. Yes, that should be a new I star. Thank you. Thank you. Okay? So now let's look at each of these terms, okay? So I want to write another inequality. I'm going to write f naught of x star is less than or equal to f naught of x star. The first term is clearly true, right? F naught of x star is less than or equal to f naught of x star. Let's look at the second term here. The lambdas, I know lambda star is a feasible point, right? It's a feasible for the optimal point because it's the optimum. So it clearly satisfies the constraints of the dual, which means that lambda star is greater than or equal to 0, right? Okay? Fi is also going to satisfy the constraints. X star is also a feasible point. So what is Fi of x star? That's negative, right? So lambda stars are positive. Fi of x stars are negative. So what is lambda I star times Fi of x star? Negative, right? So every single one of those terms is less than or equal to 0, right? So this entire term is less than or equal to 0, right? Because Fi of x star is less than or equal to 0, but lambda I star is greater than or equal to 0. Right? So that's less than or equal to 0. Okay? Plus, again, x star is a feasible point, right? That means that x star satisfies the constraints. What must be true for each of the hi of x stars? Exactly equal to 0, right? So that whole term is actually just exactly equal to 0, right? Because hi of x star is equal to 0. Okay? So this thing is now less than or equal to f naught of x star. Okay? So we started out with f naught of x star. We said f naught of x star is equal to g of lambda star nu star. We then said, oh, let's rewrite it as the Lagrangian. We said that this minimization is always smaller than something at any feasible point. And now we've come to f naught of x star is less than or equal to f naught of x star. But is f naught of x star actually equal to f naught of x star?
Yes.
Better be, right? So what does that mean? That means that both of these inequalities that we've written as inequalities must actually be equalities, right? So we're saying these are inequalities, but this argument shows that our inequalities Okay? Most interestingly, right, what does that mean? It means that this term, sigma, right? We argued this is an inequality, but because of the fact that this led us to f naught of x star is less than or equal to f naught of x star, we conclude that this must actually be an equality, right? Everyone see that? So this must actually be exactly equal to 0. Okay? So now each of the terms here, each term is non-positive. So to have something be the sum of a bunch of things to be equal to 0, right? I have to have something's greater than 0 and something's less than 0 so that they cancel out, right? But here I have every single term of the summation less than or equal to 0. I don't have any greater than or equal to 0 terms to cancel this out. Do I?
No.
So what is the only way in which all of this can be equal to 0? The sum can be equal to 0. Every term had better be 0, right? This implies that for every I, lambda I star fi of x star is exactly equal to 0. Okay? So now if I think about this, this is the dual variable corresponding to a constraint. This is the constraint itself. Okay? I have two numbers, a times b equal to 0. What can you conclude? At least one of them had better be 0, right? So either lambda I is equal to 0 or fi is equal to 0. Both could be 0, but at least one of them is 0, right? So if I knew fi of x star was not equal to 0, and in fact it was strictly less than 0, right? It's a feasible point. So I have a strict inequality here. This means that this constraint is this an active constraint or is it inactive constraint? This is an inactive constraint, right? When you're not at that boundary, this is an inactive constraint. If I know this is true, what does that imply? Lambda I star is equal to 0. So if a constraint is inactive, which means at the optimum point, it does not matter. Remember, we introduced active and inactive constraints 2 lectures ago? It's saying that the dual variable corresponding to it is going to necessarily be 0. If my business is not bottlenecked by the number of Merlot grapes that I have, then the dual variable corresponding to my Merlot grapes is going to be 0, right? I'm not willing to pay more to buy more Merlot because my ability to make more money is bottlenecked by the number of Shiraz grapes I have. Do you see that? So what this is telling me is it's telling me how I can think about the connection between the value of a dual variable and the value and whether the constraint is active or not. Similarly, if now I knew that my lambda was not equal to 0, right? If I had a strictly greater than 0 lambda, then I must have that my constraint that fi of x is equal to 0, right? That means that that constraint must be active. So if lambda I is non-zero, that means my constraint must be active. It must matter at my optimum solution, right? if I have a non-zero price for Merlot grapes, non-zero shadow price, it must matter the amount that I have. This property is called complementary slackness. And we will talk more about this in the next lecture. See you there.